Good afternoon, everyone. Better to say good evening. And now we are going to start the next session for today's program. And we are very happy to have Professor Aliasghar Alikhani with us to deliver his talk. And I request Professor D.K. Ganguly, our Honorable Vice President of Calcutta Mathematical Society, to kindly introduce him. So over to Professor D.K. Ganguly.
Thanks to our convener giving me opportunity to introduce Professor Ali, a good friend of mine, to say something about Ali for introduction. Professor Ali is right now is a University of Penn State University, Pennsylvania State University, USA. But he did PhD from University of California under the renowned mathematician Professor Andy Buckner, and he also my supervisor when I was in the Department of University of California Math Department. We passed many memorable days with Professor Ali at that time for some years. So Professor Ali did PhD especially on real function, especially on path derivatives and Borel function. And the path derivative that was introduced by Professor Buckner, Richard O'Malley, and Brian Thompson. And that paper was published in Proceedings of American Mathematical Society that contains 72 pages. And that is the unified approach of all derivatives. Ali did a lot of works after Buckner. Ali did a lot of works on path derivatives and published many papers in reputed journals in USA and abroad. So right now, Ali transferred this area from the dynamical system. And he worked several universities as a visiting professor, and even he worked sometimes in his own country, that is Iran. Now from Iran, he back to Pennsylvania State University. Right now, he is in State University, Pennsylvania State University. He organized many conferences, and I attended one of the conferences, that is Aliasghar Exchange Conference, that is 2012. So I request Professor Ali to deliver your lecture. I think the participants will enjoy very much through his lectures. Okay, Professor Ali.
Thank you very much. I would like to thank Professor Ganguly and the organizers for inviting me to present this talk. And I hope everything goes right. So, and we're not going to run into any difficulties. So, do you guys, everything is fine from your side? So you can see exactly, because that's exactly what I have. So I have the full screen. Is everything is fine?
Yeah.
Okay. All right. So the overview is that I want to talk about, some part of discrete dynamical system. Then after that, I will go to a problem which is very close to my heart, and that is related to fixed point theory, common fixed point problems. And then we go to the dynamics of continuous functions, some of the dynamics of the continuous functions. And basically today, we're going to talk about this 4 parts, dynamics of compositions of continuous functions. And then the next lecture, which is tomorrow, I'm going to talk about the dynamics of bare one function. So basically similar ideas, similar thinking, but regarding of the bare one class of bare one functions. Okay. Discrete dynamical systems has always been a part of what is called discrete dynamical system, has been a part of mathematical analysis. And lots of people in the past, they have worked on these things. However, it was not called by this name. And the interest to this area is started with the paper of Robert May, which it was published in the Nature, Journal of Nature, and the title is Simple Mathematical Models with Very Complicated Dynamics. In this article, Dr. May outlines several areas of the social and physical science where iteration problems play an important role. Often these problems involve continuous functions, which are defined on a compact set and mostly a compact interval. And the study of the dynamics of these functions involves the study of the trajectory of x and their f, which is the sequence x, f of x, f of x, which we call it f2 of x, f of f2 of x, which we call it f3 of x, and so on. It turns out that the dynamics of a real function is completely determined by the structure of the omega limit set, which is nothing more than the cluster set of the sequence. Okay, so here the notation, see, basically I, what we mean by I, it's the compact interval, and sometimes 0, 1, the unit interval. F from I to I is a continuous function. F0 is the identity. Fn is the composition of the function f n many times. The orbit of f, the orbit of x at f, it should be the other way around, is x, f of x, f2 of x, and so on. This is the trajectory of x and their f. And fm of f is the set of fixed point of fm. So f1 is basically the set of fixed points of f. P of f is the union from m to 1 to infinity of fm of f, and that is the set of periodic points of f. Of course, this could be written in this form as well, which is the union of Pn, where Pn is Fn minus union k less than n of Fk of f, which it means that this is, they're basically, it stays away from repeating. So these are some of the sets that we're going to consider. So also there are other sets in the discrete dynamical system. There are lots of sets that the researchers are interested in. And the reason that they're interested in this kind of sets is because the dynamics of the function and the properties of these sets are interrelated. And the moment that we know that these sets, they have some nice properties, that would tell something about the nice properties of the function and vice versa. So a point x in the interval I is called an almost periodic point of f if for every open set U containing x, there exists a positive integer n such that fm of x is in U and m is greater than or equal to 0, then f of m plus k of x is in U for some k, but this k should be between 0 to n. So it means that for every between 0 to n, each time there is one of these guys in U. The set of the approximate periodic points is denoted by AP of f. Omega of f of x is the set of omega, is the omega limit points of x and their f, and that is all those y's that y is the limit as k goes toward infinity of fk and fk, f and k of x, which means that is a limit point of a sequence, a subsequence of fn. And R of f is all those points that they have a subsequence coming back to themselves. So is all those x's such that x is in omega of x and f. Here, you know, these things, it should be the other way around. Sometimes we write omega of x and f, which is the correct way of writing. Sometimes we put omega of f and x. That is, we mean the same thing. And lambda of f is the union of x in I of all those omega of x and f or omega of f of x. And this is called the omega limit set of f. And we call a set is called f invariant if f of m is subset of m. a strongly F invariant if F of M is equal to M, and we call a set minimal with respect to F if it is non-empty, closed, F invariant, and if no proper subset has these three conditions. Another set that is important is the set of non-boundary points of a function. A point x in I is called a non-boundary point of F if for every open set U containing x, there exists a positive integer m such that Fm of U intersection with U is not empty. And the set of all these non-boundary points of F are denoted by big omega of F. Also, a point is called a chain recurrent point of F if for every epsilon greater than 0, there exists a sequence of points xk, k from 0 to n, such that x0 and xn are x, and the distance from f of xi and xi plus 1 is less than epsilon from I from 0 to n minus 1. And of course, the set of chain recurrent points of a function f is denoted by CR of f. So this sets that we were talking about, the fixed points of f, periodic points, approximately periodic points, recurrent points of f, the omega limit sets of f, the non-boundary and the chain recurrent points of f are subsets of each other. So it's like we have f of f subset of p of f, subset of a p of f, and so on. And there are examples that shows that there are f that, like one is bigger than the other one. Okay, so let X be a compact topological space, and C of X and X is the set of continuous functions from X to X. So, and then by the pair X and F is called a continuous dynamical system. It is called a dynamical system, but because we want to be able to change f from the class of continuous function to the other classes of function, I would call this one a continuous dynamical system. So the properties of this set, as I said, these are interrelated with the properties of functions, and that's why they have been interested in these things. Some of these properties are very easy to check, and some of them it requires, some work, and some of them are very difficult to check. But the one that I have listed are the one among the easier ones, because I was trying to give a sample of these things. And for example, for any continuous function, the set of fixed points is closed. Everyone knows that. The set of periodic points, because the fixed points are closed, is an F sigma set. The recurrent points of F is a G delta set, and that is easy to show, because if we take G of X for a continuous function F, if we take G of X to be infimum of the absolute value of Fi of X minus X, when I is greater than 1, greater than or equal to 1, this is an upper semi-continuous function, and X is in R of F if and only if G of X is 0, and therefore R of F becomes the intersection of n from 1 to infinity of all those x's that G of X is less than 1 over n. So therefore, this is a G delta set. And these results that I have listed here, it could be found in the book of Bloch and Koopae, the one-dimensional dynamics lecture notes in math, volume 1513. And there are lots of similar and other results in that book, but these are the ones that I have picked. So for example, R of F, P of F is P of Fn, R of F is R of Fn, F of R of F is R of F, so it means that is a strongly invariant, F invariant. For any continuous function F, the closure of the set of periodic points and the closure of the set of recurrent points are the same. The omega limit points of a function, the omega of X and F is closed for any x, and this is f strongly f invariant. Omega of x and f, it's a perfect set when x is in R of f minus p of f. So we see that the moment that we put that restrictions that the point is not in p of f, but it still is in R of f, it forces omega of x and f to be perfect set. Lambda of f is the set of the omega limit set of f is a closed set. And p of f, if p of f, for example, wants to be equal to lambda of f, this happens if and only if omega of x and f is a finite minimal set for every x in the interval. R of f is equal to lambda of f if and only if, for example, omega of x and f is a minimal set for every set for every x in I. So the finiteness is not, it might not be there. Okay. So these are basic results, but this kind of flavors are the ones that people working in this area, they're interested. And some are very easy to check. And most of these things, when you want to, prove, it requires basic, analysis. So it's like, uses sequence, subsequence, all those kind of things. So basically, the machinery for working in this area is basic machinery. So that's why when the problem gets hard, you don't have that many strong tools to use. So omega of f is a closed set, the set of non-wandering point of f. Any limit point of the set of non-wandering point of f is an omega limit point. The set of chain recurrent point of any function, continuous function, is a closed set. And of course, if x is a point which is in chain recurrent set but is not a recurrent set, a recurrent point of f, it is in the chain recurrent point of f, but not in the recurrent point. In that case, omega of x and f is an overdense set. And one important theorem in this area, in this part of dynamical system, is the Sharkovsky's theorem, which Sharkovsky, what he did, he ordered all the natural numbers in this way, which 1 is sitting at the bottom and 3 sitting at the top. And therefore, he said that the theorem says that if f has a periodic point of n for some natural number n, therefore f has all the periodic points of order m when m is sitting to the left of n, or m is a smaller than, you can say smaller than n if we consider this one as a small order, as less than whatever. Okay, and we call a property typical, and in this area most people, they like to call it generic if it holds on a residual set. And a residual set is the complement of a first category set. So here, some of these results that I listed here, they're not they're not very difficult to prove, but they're interesting. So, and some of them are. So there exists a residual subset M of the family of continuous self-continuous maps of the I interval, such that for every m greater than or equal to 0, m greater than or equal to 1, when f is in M, the set of fixed point of fm of f, which is the set of fixed point of fm, is a perfect nowhere dense set of Lebesgue measure 0. So it means that typically these functions, they have, in terms of cardinality, their fm is big. However, in terms of topology and Lebesgue measure, in a sense, they're small. Another theorem that it was proved in 1990 by Franzova, Nora Franzova, it's a typical continuous function, has a chain recurrent sets of Lebesgue measure 0. And so combining the results of Franzova with what is up there, it says that for a typical f in C of I and I, the set of periodic points of a function, a continuous function, for a typical continuous function is sigma perfect. It means countable union of perfect sets, first category, and Lebesgue measure 0. So on the other hand, Cohen and Emma Daniello, they proved that there is a dense first category subset A of the family of continuous functions with the property that the closure of the periodic points of f is not equal to the set of omega limit set of f when f is in A. Note that P of f, it is a subset of lambda of f, and since lambda of f is closed, the closure of P of f, it is in lambda of f. But this is, there is a dense first category subset that this is a proper subset. And a very strong theorem, a very good one, it is, among other things, in this paper, Agronsky, Brockner, Laskovich, Dynamics of Typical Continuous Function, which is published in Journal London of Math Society. They showed that typical f in C of I and I has no stable attracting point, and most points in I are attracted to a Carnot set. Moreover, if A is any prescribed residual subset of I, which we could pick it up to be 0, measure, a null set, then omega of f, the set of non-wandering points of f, is a nowhere dense subset of A. And this is a very strong result, okay? Because it does, because we can pick those subsets to be, you know, like measure 0, and some of these things, because they are subsets of omega of f, some of these sets, because they are subsets, so the Lebesgue measure is going to, for those sets, is going to become 0 as well. So, and so my interest in this area is started from fixed point theory. I was interested in fixed point theory, and that took me to a well-celebrated show that, I don't know if because I don't know if I got disconnected or not. Do you hear me?
Yes, sir. Yes, sir.
Okay, well, I thought that, you know, I heard the noise. I thought I got disconnected. Okay, the reason that I'm going over this is it is twofold. One is that it gives this, you know, that each one of us that we're in this, you know, field, we come with our own point of view because we have been in different part of mathematics, and suddenly we get attracted to what is called dynamical system. And the second thing is that there are some good problems here that I am trying to advertise and hopefully get some people interested in. And the common fixed point conjecture, see, Eldon Dyer asked in 1954 that if two commuting continuous interval functions must have a common fixed point. In 1955 and 56, Alan Schultz and Dobbins independently asked the same question. Of course, at the time, there were some results regarding of commuting rational functions, especially the polynomials. And the people, they knew the results of those results. For example, in HD Block and HP Tillman commutative polynomials, they knew that if two polynomials, it is there, and it's even before that is in the J.F. Reed paper. You can find things in this direction that when two polynomials commute, they become Chebyshev. They should be Chebyshev polynomials, and they do share a common fixed point. So, but the type of functions that at that time people, around 50s and even during 60s, the type of functions that they could write and they could commute, they were this type of functions. See, f of x like 2x when x is between 0 and 1, 2 minus 2x, or g of x being like the other one. And these are the functions that they would commute. And of course, it's very easy to see that they have a common fixed point. 0, for example, is a common fixed point of these functions. And they could not come up with the really sophisticated function that they could commute and would have a fixed point. So this conjecture was the center of a study for a lot of people and produced lots of partial results by some serious mathematicians at the time that they were working in the functional analysis and real analysis, in those areas. And then, because these sort of functions, if you pay attention, we see that the interval 0 and 1/2 goes to the entire 0, 1. The 1/2 and 1 goes to, the entire 0, 1. And the function on those intervals is 1, 1. So this led for the function to talk about commuting full functions. And they define a full function as a function that is, if we can divide the interval into finitely many subintervals, and on each one of those subintervals, f is a homeomorphism that is called full functions. And then they showed that it was Cohen that showed that if two full functions they commute, they have a common fixed point. And later on, it was shown that it doesn't have, both of them, they don't have to full, as long as one of them is a full function, that's good enough, and they have a common fixed point. So I have picked this one here. And A.J. Schwartz was able to show that if one of the functions is C1 is C1 of I, and I, it means it has derivative, continuous derivative, and it commutes with the continuous function f, then those two, they should have a fixed point. And finally, Honecker and Boyce in 1969, both of these two papers are published in Transaction of AMS. They proved that they answered this question in negative, and they constructed two pairs of commuting functions, continuous, that they do not share a common fixed point. So I was interested in this problem. Of course, when I was interested in this problem, this was set out. So the conjecture was done, but I wanted to see the trend and have, the construction was, done. And when the first thing that caught my eye was that when the function was the construction, which I'm going to go over it, like at least the sketch of the construction, they had common periodic points. So that was the start. So the construction is given in such a way that, basically in order to construct f and g, they construct two sequences, fi and gi. And fi and gi, it comes with a set of a stable point si. So fi and gi is associated with a set of a stable point si. And as I increases si, it expands to xi plus 1. So si is a subset of si plus 1. And also fi plus j of x is fi of x, and gi plus j of x is gi x. So on si, fi and gi expand as I expands, as the indexes become bigger and bigger. And for this form, this functions, the sequences fi and gi, they have the property that the composition of fi and gi plus 1 is the same as the composition of gi and fi plus 1. And the sequence fi uniformly goes toward f, to function f. The sequence gn uniformly goes toward function g. And since they are the uniform limit of continuous functions continuous, f and g becomes continuous. From the relation fi or gi plus 1 equal to gi or fi plus 1, FOG becomes equal to GOF, and this, basically these two functions that is constructed in this way, they do not share a common fixed point. Okay, so we see that these two, they have 0 and 1 as periodic point. If you look at the construction from the beginning, you see that 0 and 1 is a periodic 2 for any of those Fi's and Gi's, and therefore is a common periodic point for F and G. So the question is that, do commuting self-maps of an interval have a common periodic point? And I worked on these problems, and there were times that I was convinced that the answer to these things is, like the answer is no. We could come up with, functions that they do commute. And the more that I got involved, it was apparent that this is answering this question. It is very hard, as it was for the case of the common fixed point problem. Another question that I was concerned is that now that we have a pair of continuous functions that do not have a common fixed point, then how many of those we can have? So do we have, in another word, for example, in the language of category, can we say typically commuting continuous self-maps of intervals do not have a common fixed point? And from the construction, when we look at the constructions of Hoenecke and Boyce, we see that the construction is very similar. In a sense, it goes along the line of the constructions that we have seen for making like non-differentiable function, nowhere differentiable function, and those kind of things. And those functions, typically, for example, we know that typically a function is nowhere differentiable. Typically, a continuous function is nowhere differentiable. So it is very likely that the answer to that, how many of those guys we have typically, that it means continuous functions, probably commuting continuous functions on the intervals, do not share a common fixed point. And that is the one that after many works that I did on these problems, I believe in it, and that's why I conjectured it. And I know on the side that some people, they have worked on it because I've been in touch with me, but unfortunately, they have not been able to solve the problems or get any results. That's why there's nothing out there. Okay, now let's look at some of these things. In 1998, I showed that if F and G are two commuting continuous self-maps of the interval, either F and G have a common periodic point, or F and G should have periodic points of all even orders. So we know that, so from the dynamical point of view, see, a function that has all the periodic points at the powers of 2, h of f is 0 if and only if f, the topological entropy of f is 0 if and only if f has only periodic points of powers of 2. So it means that this problem is very related to the dynamics of the functions of f and g, especially when we are considering finding an example for the common periodic point problem. And also in 2003, among other things, this is like that f and g have a common periodic point for two continuous self-maps of the interval, or for any two positive integer m and n. If we look at this level set, a, m, n, as all those x such that f n of x is equal to g m of x, then for any x in here, omega of x and f is a perfect nowhere dense set. And this also, if we pay attention after, we look at the Bruckner and see their chaos, definition of chaos for functions on the continuous interval, that shows that this has that sort of essence of that kind of things. Of course, it has it on a restricted interval, which in this case is a restricted set, which is in this case is am of n. It is not the entire interval, and that's why, but so it is a little stronger than that. And so that is another thing that shows finding a counterexample. Should be difficult because we have to look among the functions that they commute with each other. So this family of functions in the sense of category is a small inside the families of continuous function. And on the other hand, we have to look inside the families of functions that they have positive topological entropy, which it means, you know, a big family of functions. We have to look through that. Okay? So here, so basically, if we are looking for functions that they do commute and do not have a common periodic point, we have to look inside functions, class of functions that they have positive topological entropy. Not only they have positive topological entropy, FOG and all the compositions of F and G in any order, they should have the positive topological entropy. So in related to this ones, it asks, so here I could, you know, someone could ask that, okay, if F has positive topological entropy and G has positive topological entropy, does FOG have a positive topological entropy? Or, you know, what is the relation between the topological entropy of F and G and FOG? And we're going to talk about this a little later. So Canevas and Linero, they, on the nonlinear analysis, you know, in 2002, they considered this problem because as we saw, it's, you know, like the positive topological entropy, we have to look for F and G and all those functions that FOG also has positive topological entropy. Not only FOG, like F a square or G a square, or, you know, all those things, they have positive topological entropy. And then they showed that if F and G are C of I and I, be two commuting maps. So if they commute and F and G share a periodic points of order 2 to the k times p, which is also, this is a criteria that if any of those functions that they commute, if they do not have a periodic points of this order, they should have a common periodic point. So in this case, they showed that in that case, the topological entropy of FOG is positive. So it means that for the class of functions that we are looking to find these counterexamples, as long as F and G, they have positive topological entropy, then the FOG will have the positive topological entropy. Because if this thing does not happen, it means they have a common periodic points, and our effort is dead right there. So another thing is that so here, after that, I've looked at, okay, let's consider these two metrics, the sup metric for the continuous functions. I've called this rho 0. And the metric for C1 of I and I, which is the sum of the sup norm of the distance of the functions, F and G, and their derivatives, F prime and G and F prime and G prime. And we know that C1 of I and I with this metric is a complete metric space, as is C of I and I with rho 0. And so the question that we could ask is what typically we could say about element of C1 of I and I. Okay, and so do they have, so all those functions that they commute and they do not have a common fixed point, that is where the size comes. That was what I was talking about. Can we say typically these functions, they do not share a common fixed point? Okay. And can we have a pair of commuting continuous interval functions with no common periodic point? That's another thing that we said. Of course, we said that I have conjectured that typically continuous self-maps of intervals do not have a common fixed point. And if we can come up with an example, which even that is difficult, still someone could ask that is typically that is the case, which would be a lot more difficult. And sometimes, solving a harder problem maybe is easier if someone could show that generically commuting functions do not have common periodic point. So that answers the first question. But it's usually these things are hard. And now let's go back to A.J. Schwartz's results, which it says that if f and g commute and g is in C1 of I and I, f and g, they should have a common fixed point. So that led me to get that basically we can show a lot more than that. And we can show that if f and g commute, either they should both have a common periodic point, which is a little, is not as much as fixed point, but, common periodic points, or there should be a perfect set in the set of fixed point of each one of those things. So f of f is, in terms of cardinality, f of f and g, f of g, they should be big. Okay? And this basically, it makes lots of those functions that they were the center of focus on the 60s, in mid-60s and 60s, because they had their set of fixed point was finite. Therefore, the common periodic point part, it is basically easy. It comes out of this one right away. And sometimes among those common periodic points, you could, that's where the people, they were searching and they were showing that there is one fixed point and there is a common fixed point. So the question is that for f in C1 of I and I, is P of f a countable set? And we showed that typically that is the case for continuous functions. This is a result that, I have the proof here and the proof is different. But when I was giving a talk in Spain, it brought up to my attention that the outcome of some of these things, that typically C1 of I and I should have countable set of periodic point. That comes out of a theorem is called the Jacobson theorem, and which I wasn't aware of. I had never seen it. I was not aware of that. And apparently that theorem, then later on I searched for it, and apparently the proof of that is in Russian. And I could not, so to this date, I have not seen the original proof and to see how it is done. And the part that I have seen is basically like they use a lot of machineries, and then as a result, as a corollaries or results, outcome, suddenly they get that this is, like countable. So I think the proof that is sitting here and the proof that I have done, even though that this was done before, I was informed about that, because it doesn't use a lot of machineries and it's so basic. That is the part that, it probably could help sometimes to generalize. And another thing is that this proof, as I've seen in here, look at here, if let n be greater than or equal to 1, and f be a differentiable function with bounded derivatives. If fn of f is not countable, then there exists an x0 in I, so that fn of x0 equal to x0, and the derivative of fn at x0 is equal to 1. So it has a point that the nth derivative at that point is 1. And this is the base of, these proofs. In the case of, for example, C1 of I and I, there is a finite. If fn of f is finite, we can get that. Okay, so in the case of C1 of I and I, our life is slightly easier, but there we can get, and this is basically it, the whole idea is that for a function, I approximate the derivative of that function because it's continuous with a polynomial, and then by this way, I create another polynomial which is not far apart from f, and I've called that one p, and therefore we show that, like there are certain conditions that we need. We want our functions to be inside the interval. So we see that all functions that they hit the endpoints of the intervals, this set in terms of category is not big, so we shouldn't worry about that. We also show that for n greater than 2, if f is in C1 of I and x0 is in Pn of f, which it means the periodic points of order n for f, and the nth derivative at x0 is 1, then the orbit of that point, the orbit cannot hit the endpoints. So it has to be inside the interval I. And for the 2 periods, either they have to be inside the interval, or they have to, so A has to go to B, B has to go to A. So it cannot be f of A should be equal to B, f of A should be equal to A. And those sets, see, I've called it M21, these are not that big also in terms of categories and over dense set. So we shouldn't worry about that. As far as when we're considering typically, we shouldn't worry about that also. And in this way, we have showed that the typically elements of C1 of I and I, they should have a countable set of periodic points, which right away it gives a result as that, if any, the Schwartz result, it comes right away after that. So if one of our function, it is in C1 of I and it commutes with, let's say, G, then if we start with fixed points of f, because so we can show that here we said that because it's a countable set. On the other side, if it does not have a common periodic point, a common periodic point is not, because we have started on the fixed point. If it is not, it should contain a perfect set because it should contain a minimal set. And that means that because it's countable, that's not going to happen. So therefore, that means that that fixed points of f has to be a periodic point for G. And similarly, there are fixed points of G that should be periodic. And then we can start from there to show that they have a common fixed point. So this is how this is done. Yeah, these are the proofs of these things. Now, so in order to prove these things, I showed that f is in C1 of I and I, then there exists a residual subset M of C1 of I and I such that for every f in M and M in N natural numbers, Fm of f is finite. And from there, I showed that it has the set of periodic points is countable, which is Fm of f being finite is a little bit, it doesn't come out of the ones that I have seen at least so far. Doesn't mean that it is not, it doesn't come. I could be wrong because, I do not know much about, the original proof of Jacobson. And I would, my Russian is as good as my Chinese. So I don't know either one of them. So I have not been able to, to see what's going on. Now let's go to the notion of chaos. For the notion of chaos, as many of you guys that have worked in this, in the areas of dynamical system, you see that there are lots of different notions of chaos. And these are 4 of them, which is pretty popular. And the last one is more popular among the people that are interested in real analysis. And that's why I am more interested, even though that probably the people that are working in the other part, maybe they are less interested in that. But these are four kind of chaos. One is called positive topological entropy, Lie-Yor chaos, Divani chaos, Bruckner-Seidel chaos on the unit inner wall. Okay, so the positive topological entropy started with Bowen 1971, Dinaberg 1969. They showed that is the exponential growth. The positive topological entropy is the exponential growth rate of the number of essentially different orbit segments of length n. It measures the complexity of the orbit structure of a dynamical system. Before getting into that, I have to point out that all these notions of chaos, they involve the omega limit set somehow, because they are involved with the trajectory of x and their f. And they look at the same problem from with different glasses, different point of views. And all of them, they're pretty much, they focus on the same thing. So for the positive topological entropy, let x and d be a compact metric space, and f be in C of x and x. For each n in n, we define dn as the distance between the first I iterates when I is between 0 and n of f of x and f of y, fi of x and fi of y. So this is dn. And for any epsilon positive, a subset E of x is said to be n epsilon and f separated if for x in E and y in E, when x and y is not equal, the dn of x and y is greater than or equal to epsilon. And the cardinality of this set we denoted by n of epsilon and f, which is the maximum cardinality of this set. And the topological entropy, which some books they show it with E and T of f, H of f, that is limit as epsilon goes towards 0 of the limit sub at n go toward 0, n goes toward infinity of the logarithm of n and epsilon and f divided by n. And this is the topological entropy. There is a huge difference between the dynamical properties of a function if the topological entropy is 0 or positive. So even though that the topological entropy of a function, it is bit bigger than 0, bigger than or equal to 0, and less than or equal to infinity, there is a huge difference the moment that it jumps from 0 to a positive. Of course, for piecewise monotone maps, if Cn of f is the number of intervals of monotonicity of Fn, then the topological entropy of f is the limit as n goes toward infinity of the logarithm of Cn of f divided by n. So for that, it is much easier to find the topological entropy. I honestly, in function theory, the people that are familiar with functions of bounded variation, they know that the variation is also defined in terms of the Banach indextrix, if I'm pronouncing it correctly, which it is somehow the level sets. And this tells me that there should be some sort of, at least for the continuous functions, maybe there is some other definition related to that Banach indextrix and the positive topological entropy. There should be something there, because these are, when it comes to those, at least when it comes to the functions that they are piecewise monotone, they're so similar. So it should be something there. And so The next one, it was so Fedorenko, Sharkovsky, and Smithal, they have given a characterization of weakly chaotic maps of the interval, which is published in the Proceedings of AMS. And in that paper, they give lots of useful characterization of non-chaotic functions. Of course, the moment that we say non-chaotic, you have to pay attention. What do they mean non-chaotic? In what sense they mean non-chaotic? And I think they're considering in the Lee and York sense. I think, if I'm not wrong, because I have looked at that paper a long time ago. So h of f is 0 if and only if, yes, Lee and York, as it's down here. H of f is equal to 0 if and only if f restricted the set of chain recurrent of f is not chaotic in the sense of Lee and York. So that is a characterization of zero topological entropy. H of f is equal to 0 if and only if each periodic point has order a power of 2. That is, f is a 2 to, if either is a function of 2 to the infinity, it means it has all the powers of 2 periodic points, or f is a 2 to the n function. It means it has periodic points of powers up to 2 to the n for some n. So Bruckner see their chaos, introduced their own chaos, and that paper is a big paper, very, very interesting paper. It's published in Pacific Journal of Math, and it was published in 1992. And it looks at chaos in terms of the behavior of the map, which takes x to omega of f of x. So this is how it used here. I'm using x and f sometimes instead of f and x, but that is in the title of their paper. So it means it is used both ways, these things. So Bruckner and Sider introduced their chaos, and on the idea that points arbitrarily close together can have omega limit sets that are far apart. And of course, in a paper before, it was shown that omega of x and f and x is in I is close in the metric space of the subsets of I endowed with the Hausdorff metric. So this is a metric space, a complete metric space, and the continuity. And so this is a metric space, so we can talk about the continuity of these functions, the upper semi-continuity, lower. Of course, this is set functions, but we can talk about the upper semi-continuity, lower semi-continuity, continuity of those things, and they use that to define their kind of chaotic behavior. So the xy continuity of the sequence Fn, n from 1 to infinity, implies that orbit of many points, orbit of nearby points x and y stay close together with the continuity of omega of fc, that the xy continuity shows that. The continuity of omega f, it shows that the cluster sets of these things, they stay close to each other. The omega of x and f and omega of y and f, they stay close together. Okay, so it's a slightly, thanks. And Bruckner and Hu, they showed that omega, if omega is continuous, if and only if the sequence Fn of iterates form an xy continuous family of functions. So the continuity of this one, it is equivalent, even though that it looks a little bit more general, but it is equivalent to the sequence Fn of the iterates to be xy continuous. Okay. And if omega of f is continuous, they showed that, still this is Bruckner and Hu, showed that f is a 2 to 0 function. It means that the only periodic points are the fixed points. Or 2 to the fun functions. The only periodic points are fixed points and periodic points of 2. So therefore, the cardinality of omega of x and f for all x in the interval is less than or equal to 2. But Bruckner and Sider in their paper showed that these are all equivalent. Of course, some of these things it was known, but some of them they have proved that omega of f being continuous is equivalent to fn being equally continuous, omega of f2 being continuous, fixed proof of f2 being the intersection of n from 1 to infinity of fn of I, which talks about the attractors. It means all the points, they attract to the fixed points of f2, and fixed point of f2 is connected. And for all x, f2 of f2n of x, n from 1 to infinity converges to a fixed point of f2. Fixed point of f2 is connected. Omega of f is lower semi-continuous. Omega of f is upper semi-continuous. See, lower semi-continuous, it looks more general. Upper semi-continuous, it looks more general, but they are equivalent to be omega of being continuous. But rarely the continuous functions, they have omega f that is continuous. Okay, so Steele, Daniello, Emma Daniello, T.H. Steele, in Journal of Math Analysis and Application, they showed that for a typical f, the map omega of f, which takes x to omega of x and f, is continuous on a residual subset. So on a huge subset of I, it is continuous, but rarely continuous on the entire I. So it seems that the notion of equicontinuous iterates of a function when restricted to the subsets of I is somewhat a stronger condition than the continuous. Not as somewhat, it is definitely the case. For example, look at this one. When we take f of x equal to 2x, when 0 is less than or equal to x, less than or equal to half, and 2 times 1 minus x, when x is between 1/2 and 1, then if we look at s equal to all those x's such that omega of x and f is equal to 0, 1, because that f has a point that its trajectories is dense in 0, 1, so s contains that trajectory. And so s is a dense, it turns out that s is a dense because of that, and it turns out to be a G delta set. But when we restrict f on that set, the omega of f in that set, on the set S, restricted to S, is continuous. But the sequence Fn definitely is not equicontinuous. So the restriction on subsets, as we see, is not going to impose the, the equicontinuity of the iterates. And even though that by Daniello's and TH's result, Steele's result, we see that they, on a big set, they could, on a residual set, subset of I, it could be continuous. Okay. So if omega of f is continuous, if and only if omega limit set for f has cardinality 1 and 2, that comes from the Hu and Brockner's things. If lambda of f is finite, then omega of f is b1 star. A function is b1, bare 1, if it is the limit point, the pointwise limit of a sequence of continuous functions. B1's and any function which is bare 1 on any perfect set, it contains, it will attain a point of continuity. So it has a point of continuity related, restricted to any perfect set. A function is said to be in bare 1 star if on any perfect set there is a portion that f restricted to that portion is continuous. So the bare 1 star is a subclass of bare 1 functions, and any function in bare 1 can be written as a uniform limit of a sequence in bare 1 star functions. So if lambda of f is finite, then omega of f is b1 star. And Lee and York, in their period 3 implies chaos, introduced their kind of chaos, which is f is chaotic in the sense of Lee and York if there exists an uncountable set S such that limit sup of fn of x minus fn of y is greater than epsilon, and limit inf of fn of x minus fn of y equal to 0, the absolute value of that limit infinity is equal to 0 for x and y is in S. And it turns out to be, if there is only 2 points in S, that makes it uncountable. But the original definition says if there is an uncountable set such that these two conditions, if it holds, then F, it is called chaotic. If F is not chaotic in the sense of Lee and York, then omega of F is in B1. And that's where Bruckner and Cedar define their chaotic behavior. They say a function based on Bruckner and Cedar, a function is not chaotic if omega of F is not bare 1. So in this case, it shows that if F is not chaotic in the sense of Lee and York, then omega of F is B1, which it means that is not chaotic in the sense of Bruckner and Cedar as well. And as we see here, the positive, so this is true that the positive topological entropy shows that omega of F is not of bare class 1, which it means that is chaotic in the sense of Bruckner and Cedar, and shows that, and the Bruckner and Cedar chaotic shows that the Lee and York chaotic. Okay, so therefore, and Emma and Steele on approximating omega limit sets with periodic orbits, which is published in Equation of Math, they were motivated to find a simpler structure that approximates a complicated omega limit set well. So it shows that. And then they investigated the omega limit sets which are contained in the Hausdorff closure of periodic orbits. And when F is in C of I, if P of F bar is, if the closure of the periodic points is the same as chain recurrent points of F, then any omega limit sets of F is contained in the Hausdorff closure of the periodic orbit. So this is what they got. And it is proved there that the property of P of F bar being equal to lambda of F, which is the set of omega limit sets, cannot be characterized in terms of the chaotic behavior of F. So that's what they were trying to see, that they could find something that it explains well, the complicated, approximates it well. It's not going to happen. Okay. Of course, look at, if we go back to the Cohen and Daniolo, we saw that all those F and C of an I, which this is P of F bar is lambda of F, is dense first category subset of C and I. Using sufficient condition found in the theorem that we put it up there, like the previous theorem, one, we can show that for every, we show that those functions for which every omega limit set can be Hausdorff approximated by periodic orbits comprise a residual subset. So a big portion you can do it, but not, in general, you cannot find such an approximation. And at here, I want to talk a little bit about the stability. The stability concept are usually formulated in the language of conjugacy. G is near F means that G has identical iterative pattern to those of F. If nearness is measured in the metric of C of I and I, we cannot get much. And the reason is that because, for example, if we pick f of x equal to x, that function has a very simple dynamics where we can pick a function which is the norm of the function being very small, less than epsilon. So basically from x, the rho of g and f being less than epsilon. However, we can pick our g to have very complicated dynamics. So this means that a little mistakes could, when f is perturbed to g, from a simple dynamics, we could change to a very sophisticated dynamics. So the dynamics of G is not an indication of dynamics of F. So in this, because of this reason, the Bruckner, Humke, Schmidt-al, in their paper in Transaction of AMS, they were concerned with questions involving stability in the setting of omega limit sets for functions of the self-map, continuous self-maps of the interval. And in this case, they considered the set of K, the non-empty closed subsets of the interval, unit interval, or any closed interval, and endowed it with the Hausdorff metric. And they consider K star to be the set of non-empty closed subsets of K. And they put that, they define the metric on K star as, if K star is in K star, and K star then is a non-empty family of closed sets, and K star, and they showed that this K star is closed with respect to the Hausdorff metric in K, and then furnished that K star with the Hausdorff metric H star in the form that if we pick two K1 star and K2 star in K star, we say these are closed with respect to the metric H star if every single member of them, for every single member, there is one member in the other one which is closed in the Hausdorff metric H, with respect to Hausdorff metric H. And that's how they define the metric on K star. And then they showed that for a continuous self-maps, the family of all omega limit sets endowed with this Hausdorff metric because it's compact. So they showed that it's compact because they needed this. And therefore, they started working and considering the stability in this sense. Okay. Agronsky, Brockner, Cedar, and Peterson, and in the Journal of Real Analysis Exchange, they were concerned that what sort of sets they become attractors for continuous self-maps of the interval. And they show that let F be closed, then F is an omega limit set for some continuous self-map of the interval if F is nowhere dense, or F is a finite union of non-degenerate closed intervals. So in order to have that, it should have those two forms. And every non-empty compact nowhere dense subset M of I could be the omega limit sets of some continuous self-maps of interval. So of course, Sharkovsky, long before in 1968, has shown that if F in C of I and I has zero topological entropy, then lambda of F is Q is Q union P, where Q is the Cantor set and P is a countable set. And Schmidt-al and Brockner, they were able to prove the converse to this one. So if lambda of F is like Q union V, where Q is a Cantor set and P is a countable set, then F should have zero topological entropy. So they were able to prove this one, and they have good examples in their, in the papers of Brockner's and those things. There are examples that shows how they came up with this idea. In fact, that is also present in the previous paper, and some of these ideas are also present in the Agronsky's and the group paper there. However, that paper, it is long, and because it's at the beginning of these things, it is very difficult to read, but it is very interesting. So then, of course, that paper with Brockner and Schmidt-al, also they gave the same proof that every nowhere dense compact subset of I is an omega limit set of some F in C of I and I, which much simpler proof than the origin, the other one. Okay, so Agronsky, Brockner, and Laskovich, dynamics of typical continuous functions, they had shown this one. We went over this. that shows that, you know, the omega of f, we can make it a set of measures 0 if we want to, or subset of a set of measures 0. But Bruckner and Cedar, they showed that for a self-map of a metric space, C of x and x, always omega of f is B2. So omega f for any continuous function is at least B2. But if it is not B1, it's chaotic. And if it is B1 or better, non-chaotic. So, and here is the proof that I don't know if this is exactly their proof, or is a proof that later on was given by Emma and those things. But my idea is this the same thing, because the proof of Bruckner's and Cedar themselves is not, you know, I think if it is not identical to this one, is not that far. So what is the relation between the dynamics? So the question that we asked at the beginning, what is the relation between dynamics of x FOG and xf and xg when these f and g are continuous? In general, I can say that there is not much known, but there is not, comparing to what it should be known, there is not much known. And the first example to these things was given in 1972. Goodwin in topology is showing that there exists two commuting self-homeomorphism, f and g, on compact metric space, such that the topological entropy of FOG is bigger than the topological entropy of f plus topological entropy of g. Okay, so, but for piecewise monotons f and g, if h of f is positive and h of g positive, that's not the case. We cannot say that h of FOG is positive. Okay. So Bloch and Koopae in their book show that f of, the following statements are equivalent. So f has positive topological entropy, f has a periodic point with order not a power of 2, and fn is turbulent for some n in n. But by turbulent, we mean, that's the definition of turbulent, is that there are two closed inner walls that either do not intersect or they're budding inner walls. They have one point in common, such that f of I, let's call those two intervals I and j, f of I intersection with f of j contains I union j. And that is the definition of turbulence. Of course, there is also a chaos defined in terms of turbulence as well. A function is called chaotic if fn is turbulent for some n. So that is also another definition that is there. So if we take f of x is equal to 2x when x is between 0 and 1/2, 3/2 minus x between 1/2 and 1, and g of x being 1 minus f of 1 minus x, then f and g only have periodic points of order 1 and 2. So this means that the dynamics of f and g is very simple. And on the other hand, for when x is an I, fn of x and gn of x converges to the finite orbit of a periodic points. But when we look at GOF becomes this function, and we see that this function has all periods. Okay, and this function has all periods. And the reason is that because it has a period 3. See, if we look at 0, 0 goes to 1/2. If we look at 1/2, 1/2 goes to 1. And if we look at 1, 1 goes to 0. So this has a period 3, and therefore it has all the periods. And the dynamics of this function, it's the order of periodic points of GOF is the entire, this n, all natural numbers. So the dynamics of GOF is very complicated. So we find two functions with simple dynamics, their composition is complicated dynamics. On the other hand, we have two functions that their composition is positive. So this is and h of f, and let's not look at this one. So if we take f 1 minus 2x, when x is between 1/2, x minus 1/2, and g 1 minus f of 1x. So then f and g share the periodic point 1, 0, and 1/2. Then in this case, f and g, they have positive topological entropy. And if we look at the GOF, our GOF is going to be this one, which the set of periodic points is fixed points. So they have only periodic points of order 1. So the simple dynamics, GOF is simple dynamics. So therefore, in this case, we have h of f and g of f positive. However, h of GOF, the topological dynamics of GOF, is 0. For piecewise monotone f and g, Canovas and Linero showed that if f and g are piecewise monotone maps that they commute, h of f of g is less than or equal to h of f plus f of h of g. It means that if f and g, they have 0 topological entropy, therefore h of f of g is also 0. So it would lead to the same thing. Okay. And that's, I think, that is the end of my talk. And thank you very much for listening. So is there any questions or anything?
Kaushik?
Yes, I cannot find any question in the chat box. So if there is any question from the participants, they can ask.
Thank you very much. Thanks.
No, Ali.
Yes.
I think you should. Somebody may not know the typical continuous function. So you should first define the typical continuous function, because they know the continuous function, and typical continuous function somewhat different. So
no, I said at the beginning that a property is called typical if it holds on a residual subset of the set. Now, if we look at the set of continuous functions, the families of the self-map, continuous self-maps of the inner wall, if we have a subset of that family that is residual, any property that holds on that, we say that property generically or typically holds for continuous functions. So a typical continuous function is a residual subset of the family of the continuous functions.
Yeah.
Members of that family.
And it is nowhere differentiable.
Of course, nowhere differentiable functions are examples of typical continuous function. Another thing, yes, and another thing which is true about typical continuous functions, because the intersections of two residual set in a metric space is a residual set. So if I have, for example, the typically continuous functions are nowhere differentiable. It means that we have a residual subset which is nowhere differentiable. We know that typical continuous functions are nowhere monotonic. So it means that there is another residual subset of continuous function which is nowhere monotonic. So if we take the intersection of these two, it is a residual set. So we could say that typical continuous function are nowhere monotonic and nowhere differentiable. So you can, the moment that you have these things, you can take intersection, put them together, and you say, oh, it has this property, that property, and those things. But thank you for pointing out that one. Thank you, Dr. Ganguly. You always come to the help. Thank you.
Okay. But one thing that omega limit set may be finite also.
Yes.
It could be fixed. It is an almost periodic point. If it is a
no. If it is finite, it is a periodic point.
Yeah. No,
it is a periodic.
But your almost periodic point is same as asymptotically periodic point. Same.
Yes.
Yeah.
Yes.
Yeah.
Yes.
I know.
Oh. Yes, that is this. See, in this literature, depending on the training of people, they have been different ways of defining things. And sometimes when people, they look at from their point of view, the things looks, a little bit easier because they look at their focus on those things. They are not concerned. Like, for example, from the point of view of real analysts, as you are, Professor Ganguly, you're a leader. So you know that when you look at it, that things to us, when one little property is not satisfied, we're very concerned about small families of functions that, they misbehave, where in a lot of areas, as long as there is answer, they don't care. So this depends on how you look at these things. And in some of these areas, their terminology is connected to the terminologies that they have been using, where in our areas, the terminology, like, for example, we like the word typical, where most people working in dynamical system, they like the word generic, which is, the same thing.
Okay, thanks, Ali. Waiting for your next day lectures.
Thank you very much. The next lecture is very much the same thing, but we're going to talk about the bare one functions and the difficulties that arises, and what we're going to, what should it be done, and what some new results and some of the things that it has to be investigated.
Typical continuous function belongs to bare one?
I didn't understand your question.
Your typical continuous function belongs to bare one?
No. Typical, yeah, continuous functions, all of them, they are subset of bare ones. So typical, they're subsets of continuous functions. It's a generic subset of continuous. So they are there. But we can talk also about typical bare one, because bare one functions are also, we can talk about, the family of bare one function as a bigger family than the continuous function. And if the dynamics of that is known, which nothing is almost known in that area, if that becomes known, then lots of these things that we have to worry is going to become, they're going to be answered, lots of those things, because then by making little mistakes or losing one continuity points it becomes bare one, then we're not going to worry about those things. But there is not much known, as we're going to see in the next lecture.
Okay, thanks.
All right. Any other question? Oh, go ahead.
Yeah, that's inviting any other question from the participants, and I think we are looking for some questions so that it can be more interactive. I just have one query that in case of chaos, as you have introduced, that I know that from the very perspective, might be your perspective and my assumption is not matching, maybe, I don't know. But I have heard that whether I'm just talking of chaos, it should be bounded. The total concept about the chaos should be in the bounded region. So have you just any idea about this thing as you have prepared your talk in this particular way? So is it going to be bounded, or somewhere from what particular context we should consider this boundedness?
Oh, so you mean in terms? So first of all, what I have been concerned about, what we're concerned mostly is on inner walls, and on continuous functions. On inner walls, they are bounded. So that is not an issue in the case of boundedness. I mean, for the functions, if I'm understanding your question correctly.
Yes.
And when it comes to the metric space, then usually in those kind of cases, they are very careful and they put conditions on that. So they put, I have seen some conditions I cannot recall. Maybe I don't know if totally bounded. No, I don't know. But there are some. So they do put conditions that is going to that these things should make sense. Like for example, when we want to talk about bare one, for example, later on, we have to make sure that our functions are bounded, because unlike continuous functions, the moment that one point changes, our function still is bare one, and we could easily have a countable many points changes and make our function unbounded. I mean, the soup of the function unbounded. So in that case, we could run into difficulties. So we have to be very careful. In my lectures, since I mostly work on inner walls, and when we go to metric spaces, we're careful. So usually I have not, been concerned about those. But there are people that they have been concerned about at those.
I understand. So that's why I'm asking.
Okay,
Thank you very much. Yeah, thank you very much. And perhaps there is no such question. So let us thank Professor Aliasghar for his very wonderful and informative lecture. And we will be waiting, of course, for his tomorrow's lecture at the same time. So let us conclude today's entire program. And tomorrow we will meet in Indian Standard Time at exactly 5 p.m. And tomorrow we will be having two different lectures as you have been provided with the schedule. The first lecture will be delivered by Dr. Krishanu Maulik, and the second lecture will be this Professor Aliasghar. He will be continuing his lecture tomorrow. So he will start Indian Standard Time at 7 p.m. and Professor Maulik's lecture will be starting at 5 p.m. exactly. So we will be having in between 30 minutes break as scheduled from 6:30 to 7 p.m. tomorrow. So let us have the break for today, and we will meet once again tomorrow. And as I requested that please join tomorrow 5 minutes prior, and that means by 4:55 it will be okay, so that we can start the